All right, guys. So first of all, we'll start the exam at 7:30 in the morning. That'll give you 2.5 hours. You should be able to finish it in 2 hours. So like, if you feel confident, you can come at 8. But you'll only have up until 10. If it takes you up till 10 to finish the exam, then you'll have from 10 to 10:30 to finish the gen ed assessment. If you have an exam at 10:30 or whenever they start, we can do the gen ed assessment at some later date, at some later time that's convenient to you. But we'll work that out. I suspect that you'll finish before 10, and then you'll have enough time to do the gen ed assessment. It's worth 20 points, so spend some time on it as you go through. You will see a couple of questions on that you have not seen before. Don't freak out. I'm going to give everybody those questions. I sent a message out about this earlier. Phasers and stuff like that. So I said just do as well as you can. Prepare for the exam, and then you'll be prepared for that assessment. Alrighty? But, spend time on it, thinking about it. The exam itself is, it's worth 150 points, and there are 30 points in multiple choice. I think there were 16 multiple choice, and then the rest were all free response. So 120 points in free response, and it was, I think, 10 or maybe 11 free response. And the way I make those, multiple choice and the free response, is I'll pull questions from the old test, and I'll change them up a little bit. In some cases, I've just changed the numbers. Like, you'll see it'll be almost the identical problem, except it just has different numbers. In those cases, you sort of have to remember what you did before and then do it again correctly. In some cases, they're the same problem. They've just sort of been moved around a little bit, and you're asking for different things with slightly different procedure, but it's still the same topic. You'll follow me? Like, you still have to use the same skills in order to solve that problem. So if you understand all the problems, then you'll be good to go. So I would just focus on the 4 exams that we did. Today I just want to go through the 4 exams and answer questions that you have. So yeah, so y'all shoot about questions. You want to start with exam 1 or exam exam 4? Exam 1, okay? We'll start with exam 1. All right, so what on exam 1? I'll sort of flip through. So we got electric fields here. There were some simple kinematics there. What's this? Electric fields. We had similar things with electric potentials on the next test. The acceleration due to gravity, figuring out what, using Gauss's law. This is the shell theorem, basically, and drawing electric field lines for a configuration of charges. Anything on it, that exam 1 that you guys want to look at more closely or that you're having trouble with?
Gauss's
law. Yeah, so Gauss's law. Really the hard part on this is just knowing sort of what is the type of Gaussian surface to use, and then knowing what the area of that surface is. So here we have the cylinder of mass. It has a radius and mass given. What is the acceleration due to gravity at the surface of the cylinder? And show all the steps that you use to get G. So in this, you want to start with Gauss's law. Gauss's law says that the flux is equal to negative 4 pi G times the mass inside your Gaussian surface. And remember, flux in general. Now, the idea of flux comes up a lot in these chapters, whether it's gravitational flux or magnetic flux. But remember, it's equal to G dot A, where G, which is the field, the gravitational field, or in some cases, like with the magnetic fields, it works out the same way when you want to know the flux. And area is the area vector. Now, you take the dot product here, and that comes up later when we do, that other law with the charges, the enclosed charges. I guess that's Gauss's law too. But anyway, we'll want to solve this for G. So we would say G dot A. I'm going to lose that because the dot product, because our area vector, which is perpendicular and away from the surface, is in the same direction or opposite direction. It's parallel or anti-parallel to G. So I'm just going to multiply these two values. Is equal to negative 4 pi big G times the mass inside. And then it's a matter of just solving for G. Negative 4 pi gravitational constant mass inside the cylinder. That's just the mass of our planet, or of our cylindrical planet, divided by the area. Now, for the area, we want to use the area of a cylinder. These equations for the area are on your equation sheet, as well as this Gauss's law. So we'd say negative 4 pi, what's G? 6.67, I think, times 10 to the minus 11. I think that's right. That's on your equation sheet. Times the mass inside. I don't give you the mass, but it's the same as the mass of the Earth, and that's on your equation sheet. I think it is anyway. So let's just sort of look at these equation sheets, because you'll need to know sort of what's on them. Excuse me. Yeah, here's our mass of the Earth. Here's the area of a cylinder. That's not 4 pi r squared, it's 2 pi r squared. Is that right? 2 pi r? Oh, it's 2 pi rh. I'm sorry, guys. I'm sort of sick this afternoon, so if I mess things up a little bit, forgive me. So our area is, our mass is 6 times 10 to the 24th kilograms, and then our area is 2 pi r times h. Notice that we didn't include the ends of the cylinder because our gravitational fields are parallel to the ends of the cylinder, because our gravitational field just runs in like this. And notice that that's parallel to the ends of the cylinder, so we don't include those because the dot product goes to 0. All right, and we put in those values and we can solve then for what G is. I forget what it is exactly, but we can solve for the acceleration due to gravity. Now the steps for this were to realize that my flux phi is equal to this negative 4 pi G mass times the inside. This is just Gauss's law. This is on your equation sheet. And then this is not, I don't think, that on your equation sheet, that the flux is equal to the field times the area. That's true for magnetic flux too, okay? It would be B times A. We see that a little bit later. But you're probably going to have some flux questions. They come up 2 or 3 times on the exam, so be prepared to work these type of flux problems. Okay? Is that clear, John? All right, there are several questions dealing with flux. Make sure you can do this, because you'll see at least one of them. Can I clear this out, y'all? All right. What else on this exam? Electric fields, vectors kind of thing. Now, we had a couple of things with vectors, so make sure that you can do 2D vectors. They won't be terribly complicated 2D vectors. Like they'll probably just be, you know, on the x and y axes. But if I give you 2 x and y components of vectors, or you find 2 x and y components, make sure that you can find the magnitude and the direction of that. It comes up on this exam, and then again on the next exam dealing with something else. I forget. But anyway, 2D vectors come up a couple of times. All right. What else on this exam? This one? Sure. So here we have a beam of electrons that travels between 2 charged plates. I have the speed here. And they enter a position that's equidistant. And then here's my electric field. These are negative particles. Our electric field is directed upward. That means that the particles are going to feel a downward force, and so they're going to travel down in that direction. So a couple things we need to do here. We need to find out what is the electric force, right? And Fe is equal to Q times the electric field. So Q, these are electrons, so it's 1.6 times 10 to the minus 19 coulombs times the electric field, which is 0.2. newtons per coulomb. So these things feel this force of 3.2 times, what's that, 10 to the minus 20. I think that's right. Okay, good. Thank you, Nicole. So that's the force that they feel. And then the acceleration, we want to know how quickly do they move down that distance. This distance, by the way, is 0.05 meters. But we find the acceleration. The acceleration is equal to F divided by M. So that's going to be that 3.2 times 10 to the minus 20 newtons divided by the mass, which is it's electrons. So if you have any of those particles, electrons or protons, you know their mass. Electrons are 9.11 times 10 to the minus 31. And then we would find the acceleration. And then from that, we'd need to use our kinematic stuff. So how long does it take? How long does it take for the particle to go from this point to this point? And so we'd say y is equal to 1/2 at squared. And we'd solve this for t. That's really the only kinematics that you have, finding the acceleration and then solving for t. Because remember, v0 is equal to 0, right? So that v0 t term goes away. And so I'm just left with this 1/2 at squared. So the time required to go from here to here is however I solve this for t, whatever that value is. And then once I solve it for t, then I can determine the distance that it travels from here down to here. Because it's traveling with a speed 2 times 10 to the 4th meters per second. And it is travels a distance, what was that? 0.1 meters. And so v is equal to d divided by t. And I can solve for what is that distance, which is v times t. Whatever your time is here, times your speed in the x direction right here. Now, I'll be straight up with you, you do have a problem like this, but it's made a little bit different. Like I've sort of combined it with other problems, and I've introduced magnetic fields in there as well. So it'll be similar to problems that you've seen. It's just they're sort of combined together. So I just want to tell you that so as you not freak out. But it does utilize some of the same skills, but it looks like a different problem. I mean, it looks like this problem actually. It looks a lot like it. But I introduced magnetic fields into it as well, which is something we saw in a later test. You follow what I'm saying? I'm not going to lay out the problem exactly for you, but just sort of be aware of that. That's sort of one of the ones that I changed up the most. That's why I'm telling you about it. Alrighty? Okay, what else on this test? Anything else on exam 1? Alright, well we can come back to it, but let's go on to exam 2. And if you have questions about exam 1, we can come back to it before we're done. Alright, exam 2, gravitational fields. Oh no, I'm sorry, electric fields, electric potential, work, capacitor circuits. You will have a circuit question. You'll have a couple of circuit questions, I think. But it could be capacitors or resistors, or it could be both, I guess. Like we had a couple of resistor circuits on exam 3, and then we had this capacitor circuit on exam 2. But they'll probably be simpler than the ones that you had on your exams, just for sake of time. Let's see, we had capacitors, electric fields, electric potential, work as it relates to potential. The potential, or the electric field garnered from the potential function. That's where we do the partial derivatives. Finding the electric flux through a surface, and just your basic definition of what is capacitance. How about exam 2 here? What can we look at for exam 2? Yeah, David. The work problem? Yeah. So let's see, I think it was just this problem right here, right, number 17? All right, so 2 steps to this problem. The first thing you need to do is find the potential. Now remember, this is different from electric fields. Like if I were finding the electric fields, I'd have to do a vector problem. Let me step back for just a second. If I was finding the electric fields, I would imagine I have a positive particle here. The electric field due to this particle is in this direction. The electric field due to this particle and this is in this direction. I'd calculate the magnitudes of those vectors, and then I would find the net vector, the magnitude and direction. That's electric fields because those are vector quantities. All right, electric potentials are different because they're scalar quantities. I would say at this point, what is the electric potential? And I would say that the electric potential is the potential due to the +8 plus the potential due to the -3 nanocoulomb charge. I just add them straight up. But when you do that, you would keep the negatives in those scalar quantities. The negatives don't refer to direction. They refer instead to the amount of work that's done to put that particle into place, or the amount of work or energy that's sort of encapsulated around that particle. Not direction, that's my point. So here I would have K, I'll just write in the numbers. Remember, V is KQ over R. I would have 9 times 10 to the 9th, 8 times 10 to the -9, divided by 4, that's R, plus 99, -3 times 10 to the -9, divided by 3. And often I give these so the numbers work out easily. So here that cancels, this cancels, this cancels, cancels, cancels. And I'm left with 18 minus 9. So my potential at this point A is 9 volts. Now to find the work, remember potential is energy over charge. So if I want to find the work, which is the same as energy, I would say Q times delta V. That's sort of our basic idea of what is work when it comes to electric charges. That it's the charge times the change in potential. That when a charge goes across a potential difference, it either requires work or it gains work, like it gains energy. Work is done on that object. So in this case, I have 9 volts times Q. I'm bringing a 2 coulomb charge from some very far distance away. So I say 2 coulombs times 9 volts is 18 joules. And that'd be the answer. Right. Easy peasy if you know how to do it, but if you don't know how to do it, then you know, it's not easy. That equation is on your equation sheet, but you know, that's our basic understanding of what is potential, that it's work over charge or energy over charge, and that's where that comes from. It's how we define what potential is. All right, Devin? That's a good question. All right, what else on this exam? Capacitors, electric fields, that's calculating the flux. The potential, or the electric fields from the potential function, that's where you take the partial derivatives, the negative of the partial derivatives. Capacitor circuits. '21. Yeah, we did that one before, Josh. I'm sorry. If you want, after over, we can go over it together, just you and me. All right. What else? There's a lot of good stuff on this exam. Y'all got it all? Like, you know, capacitor circuits, you know, electric fluxes, that phi is equal to E dot dA. You know how to find the electric field. It's okay if you don't. Just, yeah? Sure. So the hard part with these is just realizing what they look like. So the hard part would be realizing that I have a 2 and a 4. A 4, and then a 4, 4, and a 10. Now if you have a capacitor circuit, it'll be a little simpler than this. Like it'll be more laid out, sort of what we're accustomed to. But once you do this, you figure out, well, this is 2 plus 4. 2 plus 4, that's 6. And then I have a 4 here. This is 4 and 4. What's that? 4 and 4 in series is 2. 1 over a quarter plus a quarter. So this is 2. and then I have 10 there in parallel with that. So I have a 2 and a 4. I have 4 microfarads, I have 4 and 4, and I have 10. So what I have here is a 6, a 4, and a 2. Sorry, a 6, 4, and 12 all in series. And 6, 4, and 12 all in series. You know, I'm skipping a few steps there, but this is the basic idea. I have 6, 4, and 12. The equivalent of that is 2 12ths plus 3 12ths plus 1 12th plus 6 12ths. That's equal to 2. All right. So I have this whole equivalent is 2 microfarads. And I have a 12-volt battery. And remember, capacitors in series have the same charge. So whatever charge is on this one, Q equals CV is 24 microcoulombs, is also here, and also here. All right, capacitors in series have the same charge. They also have the same charge as their equivalent capacitor. So I have 24, 24, and 24, there, there, and there. And then anytime I get 2 quantities on a capacitor, I can figure out the third. So if I want to know the voltage, Q equals CV. V then is Q divided by C. So that would be, V would equal to 24 over 6 is 4 volts, 6 volts, and 2 volts. And that darn well better add up to 12. So 4, 6, and 2 adds up to 12. All right, once you get to this point, it becomes pretty easy, because if I have 4 volts on that 6 microfarad, I also have 4 volts here and 4 volts here, because capacitors in parallel have the same voltage. I have 6 volts here. I have 2 volts here. What about the 4 and the 4? What do I have on them? I have 1 volt each. Because they're identical capacitors, they split it up. Listen, if you see it, you'll be able to answer the question probably without writing anything down. But don't do that. Like, work it out and take a couple minutes to think about it, because it might be a little more complicated than you think. This, or you might have a resistor circuit. They work very similarly. Okay? But it'll be simpler probably than this one. But this one, once you see what it looks like, it becomes pretty simple. Does that help a little? All right. Anything else on this test? Don't be bashful. There's a lot of hard stuff on this test. It's probably one of our tougher exams. No? You want to go to exam 3? All right. Let's go to exam 3 then. Oh, what do we have here? We had multi-loop circuits, resistor circuits. Like this, combination circuit, similar on this one as it was for capacitors. But remember, the rules are different. So work through them both and make sure you understand how the rules apply regarding voltages and the currents and or the charges in capacitor circuits. Multi-loop circuits, be able to solve multi-loop circuits? Okay. So on this one, first thing you do is just to give a direction. So I'll give I1 is down. I'll just give them all down, just to be easy. Doesn't matter what the direction is. And then you pick loops to write equations for. So for example, I'm going to, I gave y'all this one? All right, I'll probably make it a little easier. I'm gonna do it, can I do it different from the test? Just to make solving it a little easier. I'm going to get rid of this one, that resistor.
Keep messing up is, like, I choose my direction, and when I do it, I always put a minus, like minus I1, whatever. I always mix up the minus and the plus. Right.
That's how you make mistakes. Now, I'll look at your equations, and if that's your only mistake, then I won't count off, of course, the full thing. But one of the most important things I want you to do is be able to write the loop rules correctly in the junction rule. So go back and review over that. Make sure that you know how to write the loop and the junction rules. let's do it here. So I'm going to pick a loop. Let's pick this loop. I'm going to pick a direction to travel in that loop. I'm going to go in this direction. So my equation is going to look like this. I have plus 4 volts. That's because I'm going in this direction from low to high potential, from little to big. Minus 1I1. It's negative because I'm going with the current. The current is going through that circuit, and I'm traveling with the current. So the resistor sort of does what it's supposed to do. And then I have plus 2I2. It's positive because I'm going against the current as I travel up this branch, and that's all equal to 0. Let's now look at the left loop right here. I'm going to go in this direction. So I have plus 2 plus 2I2 equals to 0, and then do the junction rule, pick a junction, incoming currents equal outgoing currents. So here all of my currents are incoming. I1 plus I2 plus I3, that's all equal to 0. This one's easy, and if I give you a multi-loop circuit, I'll make it easier just for the sake of time. This one's easy because I got rid of this resistor. And so the equations are just easier to solve. I don't want you wasting a lot of time on algebra. So here I'll solve for I2 first. I2 is equal to -1. That means I'm going right. I2 is 1 amp, but it's up. I chose the direction incorrectly. But remember, I keep that -1 throughout my calculations. So now I take this -1 and I plug it in up here, and I get this. I get 4 minus 1I1 minus 2 equals 0. It's 4 minus 2. I1 equals 2. So I1 is 2 amps, but it's down. And then I can just take these and solve for I3. So I3 is -I1 plus -I2. I3 is going to be -2 plus 1, -1 amps. Carrying my negatives down. -1 minus 2 was -1. So it's 1 amp. I3 we chose to be down, so it's going to be up. If I give you a multi-loop circuit, it'll be about that difficulty as far as solving the equations, right? It'll be missing a resistor in one of the loops, and if you see that, then you know to use that loop because it makes the equation just a single variable equation. It's a lot easier to solve. All right? All right. Watch those equations. What else on this exam? Do you know your household circuits? It might be multiple choice, might be on the test. Know how to do your cross products. We had cross products come up 2 or 3 times on exams, so you'll definitely have to do a cross product. Either the force on a free charge or force on a wire like we had on the last exam. You'll have some right-hand rule. I didn't give it to you as a free response, although, you know, with the cross product stuff, it's required for you to do the right-hand rule if you don't know your IJK cross products. I don't. Some of y'all memorize these. Anything else on this exam? Are you about to ask something? Yeah. No. All right, we can come back to it if you have burning questions, but let's go on to exam 4. This one we just had. Mass spectrometer. Make sure you know your LR, LC, and RLC circuits, what they do. Like we had that graphing problem. This one was, you did pretty well in this exam as a class. And mostly it was just sort of knowing the equations. So look over that equation sheet, make sure you know what to do with these circuits. Make sure you know how to do Faraday's law. Here's a LR circuit. That's the one where it swaps that energy back and forth between the capacitor and the resistor. Oh wait, no, I'm sorry, no it doesn't. That's the one where you have a growth or a decay curve, the exponential growth or decay curve. Which one swaps the energy back and forth? Do y'all remember? The LC circuits, right? When you have a capacitor that has the electric field energy and the inductor, the L, that has the magnetic field energy. Most of y'all did pretty well on this one. The hard part on this one was just figuring out the vector notation for the wire, right? Where you do the delta X for the I component, delta Y for the J component to express the X and Y components of that L vector. Like I said, know your different circuits, sort of what they do qualitatively. What on this exam? Yeah, Kyle?
Number 3. Why is it
Number 3? Oh, this one? Well, let's see. So I need to first figure out, there are two parts to this right-hand rule type problem. First, want to figure out what is the direction of the magnetic field that caused this to travel in this direction. So I know that V is down and the force is to the right. So the magnetic field must be out of the page. So here my magnetic field is out of the page. On this side, it's going to be into the page. But where this charge is going is going to be out of the page like that. Again, V is down. The magnetic... I'm sorry, that's backwards, right? Did I do that wrong? V is down. Yeah, it should be into the page. Sorry about that. So the opposite of what I said. It's opposite day, Nichols. Now follow what I did there. I have V is in this direction, F is in this direction. What is the direction of the magnetic field? Yeah, and it's into the page. All right, and now the second part of this is figuring out what current generates this magnetic field. The current would have to go like this to give a magnetic field into the page and out of the page. So it would be to the left. Is that the right answer, to the left? Yeah, so that's a good right-hand rule problem. I like it because it involves both of our ideas about magnetic fields and forces. I'm pretty sure it's on the test. I'm not certain, but I'm fairly certain it is. All right. What else here, people? Yeah, so this is the LR circuit. So some of these are really simple, and they were just sort of very quick answers. So the equilibrium current, when you first turn this thing on, the inductor impedes the current. Because it's like it's going to push back on that current as much as possible because it's getting this increasing magnetic field, and it's going to push back on that by Faraday's law, which is like a number 8. So when it's in equilibrium, though, the inductor is just like a wire. So the equilibrium current is just going to be I equals V over R. And then it's like the inductor is not even there. So that's going to be 10 over 1, or 10 amps. That's my equilibrium current. How long does it take to reach that current? Well, we have to find the time constant. The time constant is L over R. We had this for RC circuits, too, time constants. L over R, that's going to be 2 seconds. And then the total time to reach that equilibrium current is going to be 10 times the time constant, or 20 seconds. All right, it's just like with RC circuits, right? Tau is RC, 10 times that is time to charge the capacitor. How long does it take to reach 1/2 this equilibrium current? Well, let's see. So when I turn this thing on, the current looks like this, I versus T. And so that is I equals 10 amps. That's my equilibrium current times 1 minus e to the minus t divided by tau, which is 2 seconds. And then I solve this for t, letting this be 5 amps. All right, need to know how to solve that for t using your natural log function to get rid of the exponential. And then when it is at this current, what is the energy stored by the inductor? Well, UL is 1/2 Li squared. L is 2. I is 5 squared. 25 joules. All right, so there are a couple things that you need to intuit here. The whole time constant business, 10 times the time constant. You got to know which of these to use because we only have two equations for the current in an LR circuit. We have this one, which is our growth function, which looks like this, and then we have the other, the decay function. That's like when you turn off the current. When you turn off the battery, the current decays slowly. It doesn't go away right away. All right? Is that good? So? All right, what else? What was that one? Potentially, yeah. Do you know how to do it? All right, so for part C, you have this I equals I max sine of omega t. And it's asking for part C, what is t when this is at its maximum value? Well, this is at its maximum value when this is equal to 1. So what is omega t when sine of omega t is equal to 1? Well, omega t then has to equal sine pi over 2, right? At 90 degrees, right, in radians. So omega t has to equal to pi over 2 in order for that to be the case. And then we would just solve this. Once we know that, we would solve that for t. We had found omega in the first part. Omega, remember, is our angular frequency. But the key here is realizing that this goes to its maximum value when this value is equal to 1. Because sine functions, they just oscillate between 1 and -1. 1 and -1. They go back and forth, back and forth. And so this is at its maximum at omega t equal 1. In fact, or at omega t equal pi over 2. It has other maximums too, right? Because if I plot this, it looks like this. It has a maximum, actually no. That's the cosine function, I'm sorry. Because cosine of 0 is 1. So this is omega t equal to pi over 2. This is omega t equal to pi over 2, 3 pi over 2. And then 5 pi over 2, and on and on. You go around the unit circle. You follow what I'm saying? I just really want you to sort of know your sine functions, you know, sine and cosine functions and how they work. That's really what I'm getting at with these problems. This chapter is really sort of all about the mathematical tools that we introduced here. They're useful. I know that you think you might not ever see them again, but they are. These things are useful to know. Alrighty. What else on this exam? Our other exams, if we're done on this one. You can just say the number. You don't have to have an intelligible question. If, say, 25 is confusing me, I can look at 25. There is no 25. So. All right. Huh? Number 11? What was 11? Okay, yeah, so this one, it was kind of like it was a cross product. F is equal to I L cross B. Kind of like on that chapter 2 exam, I think, or where we had to find the force on the free particle. But in this case, it's a little bit different because you have to figure out what L is. So L has two components, the X and the Y component. The X component is going to be 7 minus 2. in the I direction, and then the Y component is going to be -1, -5 in the J direction. And then once you get that, you get that L is equal to 5I minus 6J. Once you go from there, it becomes just a cross product. So F is equal to 1 times 5I minus 6J crossed with 2K. So that's 10I cross K minus 12J cross K. And then you need to figure out what I cross K and J cross K are. So some of you have memorized this, but I have not. I cross K, where is it? I cross K is in the negative J direction. So this is going to be negative 10J. And then J cross K is in the positive I direction. So negative 10J minus 12I. You'll definitely have a cross product. It'll be either this one or the previous one. I just want to make sure you know how to do cross products. You might have learned this a little differently in Calc 3 if you've had that yet. And that's, if you want to do it that way, that's fine with the matrices. Alrighty. Anything else on this test? Other tests? Y'all feel good about tomorrow? You know how to do number 8? That's probably the hardest question on this test. Nobody's asked about number 8. Yeah? Huh? You good on it? No, John, you're not? You don't know how to do it?
Yeah.
Huh? Alright, so here, I want to know what is the EMF induced at t equal 2 seconds. I'm going to use, what's that law called? Faraday's law. Alright, so the EMF is equal to minus d phi dt. So my flux, my magnetic flux is changing. And remember, my magnetic flux is B times A. Phi is equal to B times A. It's like that other problem we worked where we were doing G dot A, where we had the gravitational field. Here we're doing magnetic fields. It's actually the dot product of B and A. So this is equal to minus D BA dt or A minus A dB dt, because the area is not changing. And so now we want to figure out what is dB dt. The area is pi r squared. dB dt is 6t plus 4. And that'll tell us what is our EMF. It's going to be negative 4 pi times at 2 seconds. That's 12 plus 4, 16, equals minus 64 pi, which you know is about, what, 190 or so? What did I say? 200 minus 200. Now the negative doesn't mean a whole lot, but we need to figure out what is the direction of this current. Ask yourself, is the magnetic flux increasing or decreasing? What is it doing? Increasing or decreasing? It's increasing. Right? I have no negatives here. If t is 2, at t equals 2.1, the magnetic field is bigger. Right? So my magnetic flux is increasing. That means that my magnetic field is going to be opposite what it is already there. So here, it's into the page. But since it's changing, I'm going to induce a magnetic field that's opposite it because it's increasing. This is increasing, so I'm going to oppose it. If this were decreasing, I would be in the same direction. It would, the induced magnetic field would be like, whoa, come back. We want to go back to where we were. So now I want to ask myself the question, what is the direction of the current that will produce this magnetic field? It's going to be a counterclockwise current. Like that. That counterclockwise current is an EMF of 200 volts. 200 equals I times the resistance, which is 4 ohms. So I is equal to 50 amps. 50 amps counterclockwise. So a couple things we had to do. We had to figure out what is the changing magnetic field by doing the derivative of this function and then plugging in the time that we're concerned with. And then we had to determine, gosh, is this magnetic field, is it the one that's here already, is it increasing or decreasing? We decided it's increasing. That means that the induced magnetic field in the middle of the loop is going to be opposite the direction of the already present but changing magnetic field. And then by your right-hand rule, determine what is the direction of the current in this loop that generates this magnetic field. Alrighty. What else? Nicole? Yeah. Listen, if you have a question like this, I'm not saying that you are, but if you have, it'll be obvious. Look for a bunch of negatives. If you have a bunch of negatives, that means that function's decreasing. But here, at t equal 2, it's equal to whatever value it is. If you increase t to 2.1 or 3 seconds, that magnetic field is going to be bigger. So it's an increasing magnetic field. I mean, the function for that, what does the function look like? Oh, it's just a quadratic, right? Does it just look like that? I don't know. I missed that day. Something like that. It's an increasing function. Okay? Does that answer your question? But like if it was negative 3t squared minus 4t, that would be a decreasing function. Alrighty? Any other questions from this test? All right, exams 3, 2, 1. That gravitational field one? All right. I'm going to go back to that. Y'all can go if you like. This will probably be our last question unless y'all have anything else burning.
One more. Number 19.
Josh, I'm going to go to that one, okay? Yeah? Yeah. How do you do it? This is another flux one. Here it's not magnetic flux or gravitational flux, but it is electric flux. But it works the same way. Phi is equal to E dot dA. Now if you encounter one of these, just split it up into the various pieces. You got 6 pieces. Some of them will probably go to 0 like it did on this one. But just take it piece by piece. Be careful. You do top. Phi top is equal to E dot dA. We do an integral right here, a surface integral, but really all that means is I'm just doing E dot A, right? So figure out what is my electric field at the top. My electric field is equal to this value, so that's going to be negative 2I plus 4 times Y. At the top, though, Y is equal to 3 times J. Dotted with the area vector. The area is 3 times 5, that's 15, and the direction of the area vector is in the J direction. So if I want to dot this, remember, just my J's. So I have 12 times 15, so 150, 180. So that's equal to positive 180. That's Newton meters squared per coulomb. Then you do the same for the bottom. And that's going to be negative 2I plus 4 times 0, because at the bottom y is equal to 0, times j, dotted with minus 15j, because the area vector is now in that direction, the negative y direction. But it doesn't matter anyway, because 0 times 15 is 0. And then you would do similar things. I can do them if you want. But you would do similar things for the left-hand side, the right-hand side, the front, and the back. So notice here that the front and the back, what is the direction of the area vector for the front and the back faces? I, j, or k? Is what? Right, it's k and negative k. But notice here I only have I and J terms. So the front and the back, right away you can say, I don't have any electric flux coming out of those because I don't have any electric field in that direction. And so the dot product is going to be 0. You understand what I'm saying there? Nicole? Practice this. It's kind of tricky, right? These fields and fluxes and stuff. But we have several questions. We've just done, several. The one that we're about to do, the gravitational field, this one, and then the one that we did just earlier. Is that okay to stop right here? Now, once you get the total flux, you just add up all the numbers, and that total flux is equal to Q enclosed is like epsilon times phi. I forget it. Is that right? You can calculate the total enclosed charge by the flux. That's why it's useful, because if you have an unknown charge, you just measure the electric field around it, and then you can determine what is that unknown charge. Does that help you? Okay. Is that okay? I knew y'all had more questions. Oh, what test? Exam 3. Josh, we'll get to you soon, okay? I'm not going to let you go. Got it. Exam 3. Sorry, sometimes it gets locked up. Thanks too much. Okay, it's RC circuit, a particular one. This is a lot like the LR circuit that we did. It works out practically the same. So here, we want to know the time for it to fully charge. We figure out tau is equal to RC. And that time is equal to 10 times tau. R times C is 2 times 1, that's 2 seconds. So this is equal to 20 seconds. The plot, gosh, this is almost identical to that one. Charge versus time as it charges is going to look like that. Right? If it was discharging, which is not, but if it were, it would look like that. C, what is the charge at t equal 1 second? Well, for charging, Q is equal to Q times 1 minus e to the minus t over RC. Q is equal to CV from a capacitor, so that's 1 times 12 times 1 minus e to the minus 1 over 2. And that is, I don't know, whatever it is. And then D, at what time does it have 5 microcoulombs? You'd say 5 microcoulombs equals 12, 1 minus e to the minus t over 2. Let's solve that for t. Now that one's practically identical to the LR circuit that we saw before. But it's an RC circuit. You chemists, you'll do more RC circuits than P-Chem, I think. At least Dr. Lowe used to do RC circuits. I'm not sure if he still does. But it's important to understand how these growth and decay functions work. John, is that okay? All right, good. Know those equation sheets, right? Everything, most of what you need actually is on the equation sheet, but I mean, as you know, it's not all really knowing the equations, it's knowing how to apply them. All right, anything else, y'all? Other than the Earth thing? All right, let's look at that Earth thing. If y'all need to go, that's fine, I understand. Or if you want to see this again, that's fine too. So with the Earth, we want to know what is G. So we begin with Gauss's law, which says that the flux is equal to negative 4 pi G, that's a constant, times the mass inside the Gaussian surface. So INS, that just means inside the Gaussian surface. And so what I want to do is create a Gaussian surface around this mass. The Gaussian surface will have the same dimensions as the mass and the same shape and symmetries. This flux is going to be equal to G times the area. It's actually the dot product of G and A. And that's going to be equal to negative 4 pi G mass inside. Oh, look, I know all these quantities because I know the mass of the planet is the same as the mass of Earth. I also know the area. The area is going to be pi r squared times h. You go to your equation sheet. It gives you the equation for the area of a cylinder. This is our cylinder right here. Did I say pi r squared h? I'm sorry. Yeah, 2 pi r h plus 2 pi r squared. This is the outer parts of the cylinder right here, and then these are the two ends of the cylinder. But we don't include the ends because the gravitational field runs parallel to the ends. So the area vector and the g vector in the same direction, and so we don't include, or actually I'm sorry, they're perpendicular to one another. The gravitational field vector comes out the end of those caps. So we leave that off. This should actually be 2 pi RH. And now it's just solving for G. You say 4 pi G mass inside divided by 2 pi RH. The pi's cancel. H is given. This is H. The radius, it has the radius and the mass of Earth. And so those are given on your equation sheet. Here's the radius of the Earth. Here's the mass of the Earth. So at this point now you're just putting in the right numbers to find out what is the acceleration due to gravity. And in a couple of sentences, what you do is you say, I started with Gauss's law. I set that equal to my flux. And then my area is the area of a cylinder, but just the outer part of the cylinder, not the ends, because of
I was trying to add pi r squared. That's where I was messing up.
yeah, don't add the pi r squared. Actually, it's a little bit of a wrong problem because when we do a cylinder, we really do a really long cylinder, and so this problem was a little,
Ends don't even matter.
right? The ends don't matter, yeah. So this problem, if you really treated it properly, would be a lot more complicated. All right. Does that help you a little bit? Lots of fluxes and fields. In fact, at LSU, they call this course fields. That's like all they do in the entire course is just fields. They do gravitational fields, electric fields, and magnetic fields. Alrighty? Anything else, y'all? Well, get some rest tonight. That's probably the best thing that you can do. You certainly don't want to